In this video, we're going to summarize the types of hypothesis testing that we've done so far via example. In particular, so far we've looked at using a hypothesis test to test whether or not a sample looks like random draws from a specified model. We're going to do one more example of that here in this video. And then in the next videos, we'll look at other ways we can set up our hypothesis tests to not necessarily have to test this specific scenario. So I'm going to use the two jury examples we've already looked at so far. The first was the Robert Swain jury example here, and the second was the Alameda County jury example. In both of these cases, we actually knew the underlying model for the population demographics of eligible jurors, or at least we had a pretty good guess for it. And so this plot here is a way of visualizing those distributions. And the assumption was that we were taking random repeated samples from these distributions in order to compile our jury panel. So the alternative hypothesis is actually saying, well, the way we selected it was not random and identically distributed, it was biased in a certain direction. For the Robert Swain case, we said it was biased against Black people. For the Alameda County case, because we had more than just two categories, we couldn't specify a specific direction. We were just looking for any type of bias, which would mean our distribution of our sample didn't look like random draws from this known population. What I want to highlight in both of these examples so far is we had a known model, a known population demographic, and we really were using the hypothesis test to determine whether or not the sample gathered for the jury panel was actually really randomly selected from the known distribution. The significance level we chose in both cases was 1%. Again, this is really up to the context of what you are using the hypothesis test for, but this is a reasonable convention that's commonly used. Then if you think of the test statistics, just want to compare what we used. For the first test, we used the number of Black people in the sample of 100. For the second test, we used the total variation distance. I will point out that we could have used total variation distance in the case of Robert Swain. The problem if we had done that is that it would only be telling us if bias existed. We wouldn't be able to distinguish a direction because it would be counting, selection for Black people versus against Black people, and of equally in the sense that it's taken an absolute value. And so we didn't use that as the test statistic because we were interested in actually discerning a specific direction. Then you simulate the distribution under the null. So in our first case, that actually just resulted in just simulating a binomial random variable. In the second case, we simulated a multinomial random variable and then used the results from that distribution to calculate the specific statistic, which was our TBD. So the statistic in the first case came directly out of the binomial. It was actually the count, which is what the binomial gives you. Here, I get a whole array of counts of how many jurors were in each of these categories, and then I had to take that array and convert it to a statistic, which we used the TBD. In both cases, here's our distribution, and the next step was actually to calculate the observed test statistic. We saw there were 8 jurors in the Robert Swain case that were Black. We saw that the observed TBD for the Alameda jury panels was 0.14. And in both of these cases, we're looking for where this number sits in relationship to what we would expect for this test statistic to look like. Both of these cases, our observed test statistic, were very much out in the tail of our null distribution or our test statistic distribution, which leads us to become very skeptical about our null hypothesis. So we calculate the p-value, and again, that's calculating the probability of getting 8 or less in this case, or the probability of getting 0.14 or more. How do I know which direction to look? When you're doing the p-value, you're always starting at the observed test statistic and moving in the direction of the alternative. So the alternative here was going against black people. The alternative here was biased. Bias is being measured by a larger TVD. In both cases, our empirical p-value was 0, in the sense that out of the number of simulations we did, we didn't ever see 8 or less for our count. That definitely hits our criteria. It's definitely way less than our cutoff of 0.01. So we reject the null and say the data is consistent with the alternative. And we had the same conclusion with the Alameda case. Now I wanted to just review this because now I want to add to our arsenal or our understanding of hypothesis tests by looking at a situation where I'm still trying to test this type of hypothesis test, but now the unknown in question is actually going to be the chance model. It's not going to be the random sample. We'll know that the sample's random, and we're actually going to be trying to test the model itself. So this is the, let's go back. So this is what we're going to look at next. What if we don't know the population distribution? What if we want to make our best guess, take a random sample, and then use a hypothesis test to see how good our guess was? We can do this in the context of an actual historical data set. This was data gathered by Gregor Mendel, who's basically considered the founder of the modern field of genetics. And one of his experiments, he was testing the hypothesis that pea plants were either going to have purple or white flowers in a specific proportion. So his hypothesis was each plant is going to be purple with a chance of 75%, and the rest of them will be white, the chance of 25%, and this is going to be independent of the colors of the other plants. So let's see how we can set up a test to test this hypothesis. All right, so now notice, here's what our setup looks like. Again, I have a Bernoulli distribution in the sense of I'm taking random samples from this Bernoulli distribution where there's a 75% chance of having a purple flower. The alternative, we're going to not specify a direction. We're just going to say maybe this model's wrong. So the chance of purple flowers is not 75%. I'm not sure if it'll be lower or higher. We'll just leave it open to either direction. Let's just pick a significance level of 5%. Again, that's a common convention and seems reasonable for us in this case. Now we need to think about what we should use for our test statistic. So to determine your test statistic, you really want to look at the alternative hypothesis because you want to decide what values will make us lean toward the alternative. In this class, we're trying to have you set these up so that your answer is either just high or just low, not both. So given that context, which of the following test statistics could we use to test Mendel's hypothesis? Take a minute and select all that apply. All right, so the first two, the issue with the first two is if I'm just looking at the proportion of plants with purple flowers, because I'm interested in seeing any difference, I'd have to look for both low and high values to see a difference. And so I don't want to use that because I'm going to have to look on both sides of my distribution if I use that. Same thing with white flowers. This is where absolute value is going to come in helpful in our class. So notice if I take the absolute value between the percent of plants with purple flowers and 75, that's going to check both low and high values for me at once. And so that would be a great one to use. The number of different colors in the plant's flowers, well, again, this is just going to be 2 in the sense that we only have purple or white, so that's not very useful. The total variation distance between the distribution. Aha, so now think about what this would give me. If I took the total variation distance, really what I'd be doing is doing the sum. Let's actually write out the pieces. And actually, let me do it with an example so you can see. Let's suppose that in the observed data, instead of getting 0.75 and 0.25, let's suppose I got 0.73 and 0.27. So that was like my observed. I'm just making that up. So what would the TVD be in this case? Let's see. I need to take the absolute value of the difference. So here I'm going to have 0.75 minus 0.73, so that would be 0.02. That's the absolute value. And then I'm going to add the absolute value of the difference between these two, so absolute value of negative 0.02. And then I'm dividing the whole thing by 2, which is just going to end up giving me 0.02. Okay, that would work great. That's basically the exact same thing we're doing in C, except we're putting things in terms of proportions instead of percents, right? It's basically the equivalent, if you notice, of using the absolute value of the proportion. So I'll write a proportion minus 0.75. That's really what it's doing. Proportion of purple flowers. And so that's a completely valid test statistic to use. So I'd like to highlight this to show you how in the case where you only have 2 categories, the total variation distance is the equivalent of just taking the absolute value of the difference between your observed proportion and your expected proportion. All right, I'm going to use that first one that we had as answer C, but like I'm pointing out, there's other ways you could do this. The main common feature in all of these test statistics is we're looking at some type of absolute value so that I can capture both high and low differences all in one fell swoop. And now we're going to simulate this distribution under the null. So let's pop over to the notebook to see how to do this. We're going to be using the hypothesis testing notebook, and now we are going to pop down to example 3. So before you can simulate your test statistic, you actually need to make sure you're simulating it under the exact same conditions that you'll be taking your sample. So we actually needed to know Mendel's sample size before we can go simulate the test statistic. He actually grew 929 plants, out of which 709 ended up with purple flowers. So this 929 is going to be important when we actually go simulate our test statistic. We are going to let n be 929, and we're going to just use a random sample from a binomial distribution, where the probability of success, in this case a purple flower, is 0.75. Now I'm not just going to use the number of purple flowers out of 929, because my alternative was looking for any difference, high or low. So if you recall, we just chose to use the test statistic where I'm taking the absolute value between the observed percentage of purple flowers here and the expected percentage. So if I run this, let's just do a couple random draws of this. This is now, my answer is in percent, so 0.88% difference, 0.13% difference, 1.31% difference. And now you can see some possible percent differences from 75 that I could get. I don't know from this output whether or not I was above 75 or below 75 by 2, right? This was either that my observed number of purple flowers was like 73% out of my sample or 77%. That's fine, because I'm just looking for a difference in either direction. So now if I simulate this and plot it, we know that all of my values are going to be positive because I have an absolute value, and we can see it's most likely to have something really close in percents, and then I can see how this distribution changes for different values of the percent difference. All right, so this is what we would expect under the null hypothesis, that there was a 75% chance of the flowers being purple. Now let's see where our observed test statistic lies in this null distribution. So our observed test statistic is, let's say, 709 out of 929 times 100, and the difference of that from 75, it was 1.31 away. So I'm going to go plot that again on this histogram just to show you. Okay, so that's where it shows up. And then I want to think about, all right, what's the probability that I observe that or something more in the direction of the alternative? My alternative, again, was that the proportion of flowers or the chance of being purple was not 75%. So more in the direction of the alternative would be anyway this way. We would see a larger difference between the absolute value of 75 and the percent purple. So let's actually shade that in on our plot, because that here is the probability. If this null hypothesis is true, it's the probability of observing what we did or something more extreme. In other words, that's our p-value. So if we want to go calculate that, and I guess I should be very careful. This is very close to the p-value. This is really our empirical p-value because we're getting it out of the simulation. If we wanted to calculate this all theoretically, we could, but in theory, we're going to get a very similar answer. So the empirical p-value says, let's look out of all of the outcomes that we had, how many of them are greater than or equal to this 1.3. Yeah, 1.31. Divided by our total number of simulations. And when we do that, we get a p-value. We can see here visually that it's not that unlikely. Yeah, and so this has more than a third chance this could have happened. 0.3676. So this does not make my null hypothesis look ridiculous. It's quite reasonable to have the result that we observed if the null hypothesis is in fact true. So if we go back to the slides, we'll think about this in the context of what Mendel concluded. So I've summarized what we just did in the Jupyter notebook, and let's now use all of this information to make our conclusion. So we saw that the p-value, or the yellow area here, is very large. It's definitely larger than our pre-chosen cutoff of 5%, which means this data did not make our null hypothesis look ridiculous. So what we can do is say we failed to reject the null, or the data we gathered is consistent with the null. I want to be very careful here. This by no means proves that Mendel's null hypothesis was correct. This whole framework is assuming you're coming in with some default action. So in this case, the default action is Mendel is I'm going to go forward with the model that 75% of these flowers will be purple, unless I have data that proves me otherwise, or that proves otherwise. Here, our data was not indicative of something strange going on. Now, it could have just been that we didn't gather enough data to detect the difference. So again, getting a failed to reject the null really just says, well, I'm going to continue with my default action. I don't have any compelling reason at this point to change my mind. But it is in no way a proof. Unfortunately, that's basically the best we can do with these tests because there's always statistical chances that we could be wrong. So we are just making our best decision with the information that we have. So to recap, we have tested whether or not a single sample looks like random draws from a specified chance model. We've looked at cases where we're testing whether the randomness is holding true. That was the case of the jury situation. We've looked at cases where we've tested whether or not our model looks reasonable. That was the case that we just did with Mendel. Now we're going to expand our use of hypothesis tests to say, well, what if we have more than one sample? What if I have two samples? And I want to test whether or not they look like random draws from the same underlying distribution. And that is the idea underlying what's called A/B testing. We'll be covering that next.